The Hall effect is a very important application, and it's used, some of the probes that we have in the lab actually use this Hall effect to measure the magnetic field in a certain region of space. So basically you have a conductor. The conductor in this is just a part of the conductor, of course. It extends to the right and to the left. The conductor, let's just take it to be this rectangular block. The rectangular block lies in the ZY plane, the long portion of it, and then there's a small thickness in the x direction with a value h. So the height here is d, and this part is at a higher potential than this part, so that means the electric field inside the conductor is going from the left to the right. That means J is to the right. That means the charges actually move to the left, the negative charges inside the free charges. And so the current, of course, remember current doesn't have a direction, but we put an arrow here to indicate the direction of J. So the current here is to the right. If we put current between quotes, the direction between quotes. So let's put this in a magnetic field. So if you put this slab of current in a magnetic field, and the magnetic field is pointing in the minus x direction. So it's perpendicular to this slab of current wire. What will the direction of the magnetic force on the electrons be? So if you use the cross product QV cross B, V cross B will be pointing downwards, but since the charge is negative, when you multiply by Q, then the direction of the force will be upwards. So as time goes on, negative charges accumulate on the top of the conducting material. And so the force, as we said, is upwards. So the top part will be negatively charged, leaving behind some positive charge on the bottom. So what do these positive charges on the bottom and negative charges on the top do? Of course, when you have positive and negative charge, they'll make an electric field between them, and the electric field will go from the positive charges to the negative charges. So the electric field will be upwards. At some point, the electric field will be strong enough to equalize exactly the magnetic force acting on the charges, and in that case, no more charge will accumulate on the top, and no more extra charge will be left over on the bottom, and the negative charges will just move through the material without being deviated, because the two forces will be equal in this case. So the two forces are the electric force, which is Q times E. I just put EH to call it the whole electric field. And then the magnetic force is QV cross B, but since the direction, the angle between V and B is 90 degrees, so you just get the magnetic force to be QVB. So this is at the point in time when the two forces are equal. And if you cancel the Q's, then we know that there's going to be an electric field inside the conducting wire from the bottom to the top with a value B times V. So what would the whole voltage be? What if you get a voltmeter and you put one probe of the voltmeter on the bottom part and you put the other on the top part? There's going to be some potential difference because there's an electric field. So what would the whole voltage be? What would it measure? The whole voltage, the potential difference between the top and the bottom is just the electric field times the distance. And the distance is D. So the whole voltage will be electric field times D, which will equal to VB times D. Now the speed of the charges, the drift speed of the charges moving in the conductor, we can write them in terms of the current. How would you write this in terms of the current? We know that J, the current density, is I over the area. And the area is H times D. So the J is the current over the area. And we know that J also is the number of charges per unit volume times the charge of each charge times the drift speed. So here we can then find a relationship between V and the current. So actually then if you look carefully, you'll see that V is equal to the current divided by HD NQ. If you substitute this back into the equation, you get this relationship. The D will cancel with the D. This distance cancels out. You get that the whole voltage is just the current times magnetic field over the thickness times N, which is the number of charges per unit volume, times the charge of each charge. And of course, if these are electrons, then the charge is just 1.6 times 10 to the minus 19. So how could you use this in a practical way? Well, if you rearrange the terms in the equation to write B in terms of all the other parameters, then if you measure the hole voltage, and if you know the thickness of the conductor, and you know the number of charges per unit volume of this material, for this particular material, you know the charge of each charge of an electron, we know it, and you measure the current, then you can actually determine the magnetic field in this region of space. So you can use this as a probe of magnetic field. The other thing you could do is, if you rewrite n in terms of the other variables, then if you measure the magnetic field in a different way, some other technique, and you know what the current is, you measure the current, you measure the hole voltage, you know what the thickness is, you know of course the charge of an electron, then you can actually determine the number of charges per unit volume of this material. So this is another useful thing you can use this for. This is a typical example. You have the thickness given to be 0.1 centimeters, and then the height here to be 1.5 centimeters. The current is 5 amperes. The magnetic field is 1.2 Tesla. The material is copper, which means that small n is known to be this value. Then they ask, what is the hole voltage? So the hole voltage, we showed that it's I, B over H, N, Q. If you substitute the values of I, B, and Hn and Q that are given, you'll find that the hole voltage is about 0.44 microvolts. So actually it's a very, very small potential difference. So you need a very good instrument, accurate instrument, to be able to measure this hole voltage.